All right, good morning, ladies and gentlemen. Welcome to today's video. Before we get started, I'd like to thank our sponsor, Couch Potato brand snack foods, now made with extra crumbs. All right, I don't know why you'd want to advertise that, but hey, I don't make the ads. All right, so today we're going to discuss two sample t-tests and two sample t-intervals. So what I'm going to do is first run a hypothesis test on one of the sets of data that I collected from you. And after we run that hypothesis test, regardless of the outcome, we're going to run a confidence interval just to approximate the value of the parameter. So whether we reject H null or not, we're going to run a confidence interval just to approximate the value of the parameter, just as an illustration. Typically, though, if you fail to reject H null, then there's no reason to disbelieve the null hypothesis, and you wouldn't need to run a confidence interval. But again, just for illustrative purposes. Okay, so the data that we're going to focus on for my video will be the AP Stat GPA question. So what you're looking at now on the screen is, let me make sure that I just want to make sure that you're seeing my screen. Okay, so what you're looking at is the selections for what you predicted, for what class you predicted to have the greatest GPA. And so you can see overwhelmingly people selected juniors. Then in second place was that a lot of you just thought there was no significant difference. And then sophomores and seniors were pretty much equal. They were very close. And so I thought that was the interesting comparison, the sophomores and the seniors. Okay. So that's what we are that's who we're going to compare today. So I just want to set up by showing you the plan, and then we'll randomly select the data. So with this two sample t-test, I'm going to use a red pen today for all the sort of like new information. So we're going to use a two sample t-test. And my parameters are going to be mu1, which will be the true AP stat average of my sophomores. Mu2 will be the true AP stat average of my seniors. The null hypothesis will be that they're the same. Mu1 minus mu2 equals 0. And for my alternative hypothesis, I'm going to choose I'm going to run a two-tailed test. So my reasoning is your predictions where that sophomores there were almost the same number of predictions for sophomores being the greatest and for seniors being the greatest. So I'm going to run a hypothesis test just to see if there is any sort of difference. So my alternative hypothesis will be that mu1 minus mu2 is not equal to 0. So hopefully you understand this means this is going to be a two-tailed test. My alpha value will be 0.05. And since it's a two-tailed test, that means my rejection region, so that's supposed to be the t-distribution, my rejection region will be in either tail, but it will only be 2.5% in each tail, okay, for a total of 5% rejection region. All right, so let's go ahead and choose our samples. So this is the sophomore population. This is the information that was provided to me. I understand that I can easily check this claim by just looking at the population, but for illustration purposes, we're going to run a hypothesis test, okay? So since the population is kind of small, only 34, I have to choose a small sample size in order for the conditions to be met or close to met. And so what that means is I'm going to only choose 4 random sophomores. All right, so let's get those 4 random numbers. So again, there are 34 sophomores, and let me get my random sequence. I'm going to choose the first 4 that come up. Okay, so here we go. I'm going to plug these numbers. For some reason, this is not working. Oh, why did that only go down there? Sorry, I have to adjust something real quick. All right, there we go. All right, so these are the 1, 2, 3, 4 selected GPAs, 81, 84, 89, 92. Those were randomly selected. Let me write those down now. This is my sample of sophomores, 81, 84, 89, 90. Ooh, I don't know what that was. 92. By the way, I'm writing at like an angle and I'm trying to avoid contact with the keyboard. So that's why, I mean, I know my handwriting is sort of sloppy either way, but maybe it's a little extra sloppy here. But anyway, let me just confirm that those were the actual numbers, 81, 84, 89, 92. We're good. All right, let's do the same thing for the seniors. So I'm going to choose, let's go back, an independent set of random numbers. And for the seniors, the population size is only 32. I'm still going to choose 4. And I know that is greater than 10% of the population, but it's just greater. So we're still at least close to that 10% condition. So 32 for the seniors, random.org. My largest value is going to be 32. And let me get my sequence. All right. So these are the 4 random seniors. And let me pull their GPAs. Okay. Wow, some very specific GPAs here, which is fine. All right, 87.5. '89, '89. And 93.06. I'm sorry, whoever's average that is, I'm just going to write it as 93. But don't worry, in my books, you're still a 93.06. All right. One thing I forgot to do was to open my TI-84. I'm going to stop recording. I'm going to pause the recording while this is happening. All right, welcome back. I've opened the TI-84, and I've actually also entered the data into list 1 and list 2. All right, so we will use that in a moment. So, okay, there we have it. That's the plan. Let's go ahead and see if we can justify that we can use the t-distribution. Well, random selection, you saw me choose randomly for both samples, and I'm going to stress here that when you are justifying the condition for a 2-sample t-test or a 2-sample t-interval, you need to make sure that the conditions are met separately for each individual sample. Okay? The 10% condition, 4 is approximately 10% of each population. It's actually a little bit more, so we're going to have to say proceed with caution in this case. All right, the nearly normal condition. Well, n is not anywhere near 30 for either of these samples, so I need to check the normal probability plot. So let's go ahead and do that. My TI-84. I'm going to do it for list 1 first and then for list 2. So for the sophomores and then for the seniors. Let me quit out of here. Stat tests. Ooh, what am I doing? Second stat plot. And I'm going to turn plot 1 on. And of course, I'm going to go to the very last option. This is my normal probability plot. Let me quit. And then zoom 9. And as you can see, this set of 4 numbers is fairly linear. So actually the normal probability plot checks out pretty well for the sophomores. So for the sophomores, sophomore NPP is nearly linear. Therefore, sample is nearly normal. Okay, so that's how that works. Let's do the same thing for the seniors. All right, I'm going to go back to StatPlot, but I'm going to change, instead of list 1, I'm going to use list 2 because that's where the seniors are located, and then zoom 9. Okay, so this doesn't look great, but it's not horrible. I mean, it just so happens that in this small sample, we had 2 numbers that had the same exact value. So we will say normal probability plot is not quite linear, but somewhat close. This isn't really that far off from linear. Really, with a small sample, it's kind of hard to not have a normal probability plot that's nearly linear. So here we go for the seniors. So I don't want to say nearly linear because it's definitely not as close as the sophomore normal probability plot. I'm just going to say roughly linear. Therefore, the sample is roughly normal. All right, roughly, I guess, is a word that I'm using to be not quite nearly. All right, anyway, we move on. I'm totally fine if you say that you want to proceed with caution for this particular condition. So there's actually an extra condition that we need to discuss here, and that is the idea of independent groups. So is there any reason for you to believe that the GPA of sophomores has any dependence on the GPA of seniors? And if you do believe that there is a reason to suspect that, then we really shouldn't proceed with this hypothesis test, because in order for this hypothesis test to work, the 2-sample t-test to work, the 2 groups that we're studying, the 2 populations that we're studying, have to be independent of one another. And yes, you all go to Bronx Science, you're all in AP Stat, but that is the population we're studying, Bronx Science, AP Stat students. Besides those similarities, do you think that these 2 groups depend on one another in terms of their GPA? And frankly, I don't think so. So I believe that sophomore GPAs, I spelled it wrong up there. So I believe that sophomore AP Stat GPA is independent of senior AP Stat GPA. All right, and there we have it. We have our conditions either met or not met, and we've already exclaimed that we're going to proceed with caution. So now, if all the conditions are met, then we have to deal with the sampling distribution in order to calculate our p-value. So the expected value of the sampling distribution of x bar 1 minus x bar 2 is going to be 0. And that's thanks to our null hypothesis, right? We are assuming that the parameters defined above are equal to one another, and therefore the sampling distribution of the differences of samples will be centered around that parameter, that assumed parameter of 0. Okay, what we need next is the standard error of x bar 1 minus x bar 2. So before we do that, let's get the values that are necessary. So I don't have much space here, but I'm just going to write the summary statistics for these two samples. So let's call x bar 1. Let's call this S1. So I'm going to write the mean and the standard deviation of the sophomore sample. And then I'm going to write the mean and the standard deviation of the senior sample. And I'm going to use my calculator to get this information. Let me quit to the home screen. And I am going to press Stat Calc. And I'm going to do two variable stat. I'm going to enter both list 1 and list 2, and you'll see what happens. So by doing two variable stat, I can actually get the summary statistics for both samples at the same time. So that X bar is the average of list 1, which were the sophomores. So 86.5 GPA is the sample average. The sample standard deviation was 4.9329. And the units you could think of as points, right? But now if I scroll down, I have Y bar and S of Y, and those are the mean and standard deviation of the second sample. So those are the seniors. So 89.625. And 2.3585. Okay. So I'm going to use those sample standard deviations to help me calculate the overall standard error of the distribution of x bar 1 minus x bar 2, right? Because really in general, this standard error should equal sigma squared over n plus, or let's say sigma 1 squared over n plus sigma 2 squared over n, n1 and n2. And then take the square root of that sum, right? I'm taking the square root of the sum of the variances. That's how we get the standard error of a combined distribution. But in this case, I don't know sigma for either one of these populations. And so that's really one of the main reasons why I'm using a t-distribution. And in order to approximate sigma, I'm going to use the standard deviation of the samples. So in this particular case, I'm going to take 4.9329 squared over 4 plus 2.3585 squared over 4. And then I'll take the square root of that. So I'm going to go ahead and calculate that, but you don't need to see me click numbers. So I'm going to pause recording for a moment. Okay, welcome back. So after calculating the standard error, I got around 2.7339. Okay, so this is the sampling distribution that we are dealing with. And now we're going to, of course, plot our observed stat on that sampling distribution and see, well, if our assumption is true, what's the probability of observing that difference? So our observed difference, so x bar 1 minus x bar 2, and I'm doing it in that order. So it's okay to get a negative number, which is what is going to happen in this case. So I got negative 3.125 as my observed stat. okay? And as far as my test stat goes, I take the observed, I subtract what I am expecting, which is 0. I'm assuming that's based on the null hypothesis. So observed minus mean over standard deviation, 2.7339. So my test stat is approximately, let's go ahead, -3. So I'm doing this on just my own calculator. You don't need to see me and do arithmetic, I don't think. -3.125 divided by 2.7339. And my test stat is around -1.1431. All right, let's see if that is enough to reject this null hypothesis. So since this is a two-tailed test, I'm going to test the probability of observing this test statistic or more extreme in either direction. Or another way of saying it is, what's the probability of observing the observed stat or more extreme in either direction? So actually I'm going to write out both. So we're doing 2 times the probability that x bar 1 minus x bar 2 is less than -3.125, okay? But with the t-distribution, we actually have to express our p-value in terms of the test stat, because that's how the calculator needs it to be input. So this probability is going to be equivalent to saying 2 times the probability that t is less than -1.1431. All right, and let's go ahead and calculate that p-value. Now, one thing you might be screaming at this point is, what about the degrees of freedom? And that is absolutely right. I cannot calculate my p-value without first determining degrees of freedom. So I'm going to show you a little bit of sort of like a cheat. And let me actually write the degrees of freedom up here. So many of you wrote to me concerned about this long formula that was in the textbook on page 468. You're not going to be expected to memorize that formula, but if you do want to calculate a p-value by hand, here's how you're going to get the degrees of freedom for a 2-sample t procedure. So we're going to kind of work backwards. We're going to actually go ahead and run the entire hypothesis test, because when we do that, we will get the degrees of freedom. So I'm going to go to stat, scroll over to tests, scroll down to a 2-sample t-test, which is what I'm trying to run here. All right, so in this case, I have data in my lists. So I'm going to choose the data option. Frequency will just be 1 for each. My alternative hypothesis is that mu1 is not equal to mu2. And we will not use pooled data. So since we don't necessarily, yes, we're assuming that mu1 is equal to mu2. That's fine, but we don't necessarily know that sigma 1 and sigma 2 are equal to one another. And in fact, the statistics that we're using don't show that at all. So in general, we don't necessarily know that the populations are the same, even if we're assuming that the means are the same. Therefore, we will not pool the data, okay? That's different in the situation when we are dealing with proportions, but with means, we don't know that the populations are the same, and therefore we do not pool the data. All right, we click calculate, and notice the degrees of freedom comes up as 4.3035. And not only did the degrees of freedom come up, but like everything we need. We have our test stat. Let's just check that to the one we have. Yeah, -1.1431. All right, that looks good. That's what we had. We're yet to calculate the p-value, but we will do that right now. We should get around 0.3126. All right, so let's do that on this calculator. We're gonna calculate the p-value by hand. Now, by all means, when you're doing your own work, feel free to just use this p-value. Like at this point, you could just say p equals 0.3126. So at this point, you could just say 0.3126. But for illustration purposes, I'm just going to show you that we should, if we do it the long way, we will get the same answer. All right. The long way, of course, is by doing the long way is by doing second distribution. Scrolling down. TCD, oh, that one too far. TCDF. All right, our lower bound is the test stat that we are observing, which is negative 1.1431. Negative 1.1431. The upper bound will be some large number, and our degrees of freedom are 4.3035. Enter, enter, enter. And this is the p-value. Oh, you know what? I made a mistake. Hopefully you were screaming and yelling at the screen. But of course, let's go back to TCDF. What did I do wrong? Well, let's look at the statement of my p-value. I'm looking for the probability that t is less than negative 1.1431. So that number is actually the upper bound. So good job if you caught that. Now the thing is, I caught that after the fact because I saw that my p-value was so large, and typically a p-value isn't that large. You typically have something less than 1/2. So anyway, my lower bound is going to be negative 999999931. Sure. My upper bound will be the negative 1.4131. Oh, 1431. That's why I always check. My degrees of freedom are still that number. Enter. And now this looks like something more to what we should have expected. However, this is not exactly the number we have on our screen. What's going on? Well, I still haven't multiplied by 2. I have to multiply by 2 because this is a two-tailed test. So I'll do the answer times 2, enter, and 0.3126 matches up pretty well with what we have here. Okay. Long story short, let's finally finish this guy off. So let's summarize the p-value first. So since this is a two-tailed test, we're gonna summarize in the following way. If the true difference in average AP stat GPA, mu1 minus mu2. Now I write mu1 minus mu2 just to be clear, the order of subtraction. If we subtract it in the other way, you would have a positive test stat and a positive observed stat, which is fine, but just make sure that you're clear about what way you're subtracting. So if that true difference in average GPA is equal to 0, then the probability of observing a sample difference of, well, what did we observe? Negative 3.125 points, or more extreme in either direction is 0.3126, right? So that p-value is the probability of observing our sample or more extreme in either direction. I can say that here because this is a two-tailed test. All right, moving forward, now let's make our decision. Since p-value, which is 0.3126, is greater than our alpha value of 0.05, we, in this case, fail to reject H null. We do not have evidence to support the claim that there is a difference in average AP stat GPA between sophomores and seniors. Interesting. So we failed to reject the null hypothesis, meaning it's totally feasible that there is not a significant difference between these two populations. That being said, even though we have not knocked out the possibility that mu1 minus mu2 is equal to 0, I'm still going to build a confidence interval to approximate the difference. And we're going to do that in a separate video since this one is running very, very long. All right, folks. So I will see you in the next video.